Good afternoon. We are starting lecture 10 of our optimization course, and the title is the conjugate gradient method. We already have learned two very important methods of optimization: gradient descent and Newton method. So if you remember, gradient method is a simple and often rather efficient method, but it has difficulties when the level function, level sets of function become like a narrow valley, and the gradient may start zigzagging. So we told that if condition number of Hessian will be large, this what happens. Condition number is a ratio between maximal and minimal eigenvalue of the Hessian. So, and the central alternative, we then considered Newton method, which is much stronger, but Newton method requires computing and keeping a Hessian matrix. For example, if one has a problem with say 100,000 variables, which may be even not very large size of problem arising, for example, in image processing or in three-dimensional imaginary, like medical imaging, tomography, and so on. So if you have 100,000 variables, Hessian matrix will be 100,000 by 100,000, which is pretty large. It already above the limit of memory of some standard computers. And also, if one wants to solve a Newton system of equations, so the complexity of Newton's of solving system of equation in general is like n cube, where n is the dimensionality of the problem. So we told that with Zibulevsky factorization, for example, is 6 of n cube, but still this number become very large. It may take hours when n is 10,000 or something like this, and then doubling size of n will multiply by factor 8 computing times, so it become not practical for 100,000 or for million variable to talk about direct inverse of the matrix if it doesn't have some very special structure, of course. So we need methods which bring some compromise between not so good behavior of gradient method, gradient descent or steepest descent, and computational complexity of Newton method. And conjugate gradient is the central method on this line of the methods which compromise somehow. We will we will start with conjugate gradients for minimizing quadratic function, and then we will pass to general nonlinear function. Okay. So the derivation of the conjugate gradient method is is heavily based on a notion of scalar product and orthogonality, but not in a usual way, but in some more generalized way than you are used, for example, for standard scalar product in Euclidean spaces. Therefore, we will start with general definition. I just reminded you, general definition of scalar product. So, say we have vectors, A, B, C vectors. And say alpha scalar. We will consider complex numbers. Alpha is a complex scalar. And scalar product is defined by the following properties. Scalar product A and B, this is a notation, is a complex conjugate of B and A. Second property, A scalar product is B plus C is AB plus AC. Then alpha number multiplied by A, scalar product of alpha A with B, alpha can be driven out of the product, alpha scalar product A with B, and AA number 4, AA is greater equal than 0, and is 0, AA is 0, if and only if the vector A is 0 vector. And based on scalar product, one can also define a norm. I will even write it by words. One can define a norm, saying that norm of A is square root of scalar product A with itself. Okay. Okay, and so some standard examples of scalar products. Examples. Of course, if we have two vectors in Rn, I can write scalar product A, B is A transpose B is sum AI, BI. Standard example. Okay, this is first one. The second one, for example, we have a function, for example, of one variable, but it can be generalized. to multiple variables. So for example, here is an interval. We will call t. And we have functions, say f, and say some other function g, and we say that scalar product f and g is integral over this interval t, say f of x. I can say even function can be complex. In this case, it will be complex conjugate g of x dx. Okay, and many other example. But what we will be interested in derivation of conjugate gradient method is following example. So let x, y again Euclidean vectors in Euclidean space, and q symmetric positive definite n by n matrix. Then I can write it as proposition. I denote as x, y in index q, x transpose qy. And proposition is that this is a scalar product. Is a scalar product. And I suggest you at home to check all properties we already mentioned, all 5 properties of scalar product, and verify that all of them are right. So do it at home. Okay, the next part of preliminaries we will need and we will use this so-called Gram-Schmidt orthogonalization. Meaning, if we have a set of linearly independent but non-orthogonal vectors, on the basis of this set we can build orthogonal, even orthonormal set of vectors. So we are given x1, x2, xn set of linearly independent vectors. And we build orthonormal basis. Orthonormal or orthogonal. Let me think. let's go, and then I maybe will correct here. Let's see. So the general idea is, for example, I have a vector x1 and I have a vector x2. So x1 I keep as the first vector of my basis. So it will be orthogonal, not without normalization. Orthogonal. Okay, and then as instead of x2 as second vector, I will take y2, which is equal, which is I should subtract from x2 its projection on the direction of x1. I even will not write it formally here, just leave it as a picture. Okay, so what we have, y1 is equal to x1 and y2 is equal, so I should subtract from x2 its projection. So how would I compute projection of vector? So I need to have a unit vector in this direction and compute scalar product, and this will give a value. So let me write. So it will be scalar product of x2 with y1 divided by its norm y1. So it will be normalized vector. It will be a value. It will be a value, and I should multiply by this unit vector, this value of projection. So I should multiply it by y1 divided by norm y1. Okay. So, and what I have finally is x2 minus x2 scalar product with y1 divided by this squared. By this squared y1 norm squared and multiplied by y1. Okay. Over x. So what we have at the third step, we will have those two vectors, y1, say this is y1, this is y2, and we will have some vector x3, and what we will need, we should project it onto subspace of y1 and y2, and then this difference will give us y3, and so on. How can I compute projection onto subspace? I just have some orthonormal system, orthogonal basis in subspace, and compute coordinates of my vector x3 in this system, and this is the procedure. So I can write even generally. Yk is xk minus sum I is equal from 1 to k minus 1 scalar product x k yi divided by norm yi squared and multiplied by yi. So this is a general expression for Gram-Schmidt procedure. Okay. And now, what we really will need for conjugate gradient methods is so-called Q-conjugate or Q-orthogonal directions or vectors. It just means that we will need directions di and dj such that the scalar product with index q scalar product is 0. I just remind you that it's di transpose q dj should be 0. And if you have a set of vectors which are just linearly independent, we can, using Gram-Schmidt procedure, build a set of Q-orthogonal or Q-conjugate vectors. So let we have a system of vectors xi1, xi2, xin linearly independent. Then I have not enough room here. I especially kept this old formula we get on the previous whiteboard. Let's try to manage with this. Then by Gram-Schmidt I need to change my pen. Then by Gram-Schmidt, so we will take the first vector dk d1, or let me see, okay, d1 is just equal to xi1. And then I will just modify this formula and you will write it again. So I will have dk, and instead of rx I will use just xi k, and here as a scalar product I will use I will just open it explicitly, so it will be dk transpose q di here in the denominator I need the norm, and I also will write it explicitly. The norm of di squared is scalar product of di with itself. So it will be di transpose q di. And of course, multiplied by di. Sorry, I have a mistake here. This is a new vector. Say k transpose. Okay, and so we can easily obtain a set of Q-conjugate vectors when having just dk, when having just set of linearly independent vectors xi k. And what conjugate direction, as we will see right now, give us a very simple possibility of minimizing a general quadratic function. So say we have a function half x transpose q x plus b transpose x. Okay. And suppose we have built a set of Q orthogonal of Q conjugate direction. So we have a set of d I from 1 to n Q conjugate. And let's express our x in this basis. Let x is equal sum of alpha I di. I from 1 to n. How can I write f of x? F of x. First of all, what is written here is a Q scalar product. So it's half norm of x with index q squared plus the second term as it was, b transpose x. But so we can ask a question. What is the norm of a vector when we have its decomposition in orthogonal basis? And you can derive this simple formula yourself, but it's also well known that it will be just sum of squares of these decomposition coefficients multiplied by squared norm of basis vectors. So it's equal to this sum half alpha I squared norm of di. Of course, norm, everything is taken with index q, meaning that when computing norm, we use this definition of scalar product, of q scalar product. And the second term is just sum of B transpose multiplied by di and also alpha I plus alpha I B transpose di. All this I am summing. I is equal from 1 to n. And now let us put attention that each term of this sum is depending only on alpha I with corresponding value of I. So I can denote all this inside as phi I of alpha I. And then I have I can write I have function of x, but my x I have expressed as function of alpha. Just leave some space here on the left. Is sum, and leave also here space, of phi I of alpha I. So I have a function which is a so-called separable. It is a sum of terms when every term depends only on its own variable. And it's obvious when I want to minimize this sum, I can independently minimize every term, because when I'm minimizing one term and looking for some optimal value of alpha I, it will not influence at all optimization of other terms. So let me first write that this function is so-called separable. In alpha. And then, as I told, what I can do, if I like to find minimum over alpha of this function, it will be just sum of minimums. Min over alpha I. So I have a set of one-dimensional optimization problems, and this will make my life really simple. So I can start from I is equal to 1. The order doesn't matter in this case, and just do n sequential one-dimensional optimizations. One D minimizations. Or we can we call them line searches. And this is a basic idea of so-called conjugate direction methods. This method, if somebody will ask you what is conjugate direction method, this is this method. So again, we need to find set of conjugate directions. We then express our original function in terms of those directions, and actually this is just a primitive optimization, one-dimensional optimization. Of course, it can be done analytically in every alpha, because when you computed your conjugate directions, this will be a number and this will be a number, and just analytically you will find optimal values of alpha I, and then you just substitute here and get your optimal x. Now, we have derived the formula of conjugate direction method for Ex being a linear combination of directions. It's rather easy doing the similar arguments, get the result for X belonging to some affine subspace. Let me start it from the point x0 and looking x in this form. So our Ex is x0 plus linear combination of direction vectors, and then very similar arguments can be repeated, and we will get a similar idea of sequential one-dimensional optimizations. But now, what is interesting, I will ask a question: if I will do only part of those optimizations? I mean, what will happen after iteration k when k is less than n? So I have x in this form. I from 1 to k, and I did sequential optimizations. So what I can actually say that I minimized my function over all possible x's that belongs to this affine subspace, and this is this property of conjugate direction method. It's called so-called expanding manifold property. Let us put the title. Expanding Expanding manifold property. So let us define a affine subspace G is a set of all x's which can be expressed as some x0 plus some I is equal from 1 to k alpha I di. For any alpha. So all possible x's, they form a affine subspace. It's like a linear subspace shifted by the vector x0 from the origin. So we have a vector x0. Here, for example, is our origin. Let's drive two-dimensional picture. This is x0, and this is our affine subspace G. And the claim is that after step k of the conjugate direction method, after step k of conjugate direction method, we get xk will be argmin of f of x over x's that belongs to this set. Let's also give it index gk. So it's a affine subspace defined here. Okay. So we told that for x's having this expression at iteration k of conjugate direction method, we minimize over all possible alpha, or in other words, we minimize over x's belonging to affine subspace having this form. Let's ask a question: what will be the gradient after minimization over this subspace of our objective function? And the claim will be that gradient should be orthogonal to all these direction di. Let's try to see this. And first of all, let me define a vector alpha, k-dimensional vector in Rk, and let me define a metric D with the columns D1, D2, dk. And then I can write my x, put this separately. I can write my x as x0 plus d alpha. Okay. So, and what I do, I minimize over alpha my original objective function of x0 plus d alpha. Of course, when I did this minimization, my gradient over alpha should be 0. And this will characterize this new point. So let's see what will be the gradient. So gradient over alpha, one can show, and I suggest you to do this at home, will be equal to d transpose gradient over x of f x0 plus d alpha, when x is what I defined here, it's x. Okay, and this after minimization, so how can I write after minimization? Let me write that some alpha star will be argmin. Okay, so maybe alpha bar, and my optimal result of this optimization, x bar, will be equal to x0 plus d alpha bar. Okay, so what I will have, that's d transpose gradient with respect to x f, and this is x bar, my x bar after optimization. X bar is equal 0. Here should be f, sorry. Is equal 0. And let's see what is the components of this matrix D transpose. What is first component of this product? This will be D1 transpose gradient of f of x. And of course, if this is 0 vector, this should be 0. So D1 transpose gradient x f of x bar is equal to 0, and D2 transpose gradient x f x bar is equal to 0, and so on, dk. So all those vectors, dk transpose gradient of x f x bar is equal to 0. It means that gradient in this new point will be orthogonal to all directions which to all previous conjugate directions. We can write even in this form: new gradient is orthogonal to all previous directions di I from 1 to k. And this is very important property, and we will use it in derivation of the conjugate gradient method.